This slope is purely due to friction. Adding them all together, working back, you need at least 30 psi, 30 psi to push all this water through, right? So municipal water supply coming from town, if you live in an apartment or a duplex, whatever, there's a water supply that's in the yard that you have to tap in. That water supply is easily 140 psi. Inside your house, there's a reducer, which is nothing but a regulator to step the pressure down from 120, 130 to maybe more like 60 and 50s. That's what that is, to make sure you have enough pressure to provide water on the 3rd floor, for example. All right, so sometimes, if that valve in my home happened more than once, that valve, that reducer inside my house is malfunctioning, and it's not controlling the pressure, and it becomes too high. Instead of like 60 psi within my house, it may become 80. It has a water hammering effect. And if you have ever seen that, if you want to be a plumber, you have to listen to this. When you open the water one, and you shut it, all the pipe rattle, they shake. Have you ever had that in your house? That's what this is. The water supply coming to your house is too high. And it creates, when you shut the valve, it creates like a shock wave. The water stops and send a pressure pulse within your whole house back to the valve, and they resonate, and they just shake. You know? So it's not very fun when you flush the toilet at night. You wake up everyone. So this is for plumbing. Questions? Yes?
When you're looking at the actual nozzle where the water's going to come out, you have to take into account the minor losses because it's the nozzle and
That's correct.
And the velocity change.
That's correct. Very good observation. At the very end, you have a nozzle that's a K, plus you are also adding kinetic energy from a 3/4 inch pipe to a 1/2 inch pipe. Yeah. So that sudden drop has two components: minor losses plus the kinetic energy. Yeah, very good. Right. So are you comfortable with that example? Just a very simple-minded walkthrough of all the components that will create pressure drop. So one part of it is friction due to shear boundary layer. One part is due to separation in devices such as valve and so forth. Any questions on minor losses? No? Okay. So let's take a step back and revisit all the content, the new material we cover since test 1. All right. So we spent a good bit of time deriving the Euler equation. So what is the Euler's equation? Someone tell me. What is the Euler's equation? What does it assume? Do you know the name Euler? Right here, the Euler's equation. What does it assume?
Constant density?
No, not constant density, no. When I say the word Euler, I'm referring specifically a class of flow. Invisible, yes. Frictionless. So when I say Euler's equation, I'm implying, I'm pretending there's no friction. Right? So we spent a good deal of time, as well as the homework, to derive those equations. And it's nothing but just an equation of motion, or in a very loose sense, a momentum equation, but written for a differential element. That's what the Euler's equation is about. Do you remember that? All right, and we start by formulating a differential analysis, your calculus, where I have a differential element of size dx. In Euler is ds and dn. Direction along the streamline, direction normal to the streamline. And the differential calculus allows us, using chain rule, to look at the change of a quantity, theta, and how much it changed across this small element. So the right side is the delta change in crossing through this element. And theta can be pressure, can be velocity, can be energy, can be momentum. We see it all. But this is kind of the foundation. Do you remember all this? Can you do this derivation? I did one in class and you did one for homework. Right? Upon that, and all that time was spent with one and only one objective, is to separate Bernoulli from the energy equation. So where does Bernoulli equation come from? If I give you a multiple choice question and give you, or fill in the blank, Bernoulli equation come from equation of motion, the Euler's equation of motion, nothing to do with energy. And that's why we went through this derivation of the Euler, so that all the assumptions with Bernoulli can now be reinforced along a streamline. Why? Because you have to integrate the Euler's equation along the streamline. Steady, because the equation itself starts with steady assumption. Inviscid, because we are dealing with the Euler's equation assuming no friction. The incompressible assumption, constant density, only needed when you integrate the Euler's equation. It's very detailed, but I hope you should be able to comprehend that. It wasn't an original assumption from the get-go. It's only when we integrate, we have to assume the density to be constant in order to have a closed form, very nice, simple Bernoulli equation that we love to use. Right? So one more time, if you have a new problem that you have never seen before in any of the homework, what are the sequence of equation you will use to try to approach that problem? Continuity, go on. You will try to use Bernoulli if all the assumptions are met. Why? What does Bernoulli relate? What are the terms that appear in Bernoulli? Pressure, velocity, and gravity. And it's a nice closed form. No forces is involved, meaning I don't have to deal with momentum. But you will be tricked, if the assumption that cannot be met within Bernoulli, and don't use it, just like SP1. Think of other means to solve the problem. Is that clear? And heat addition or energy has nothing to do with Bernoulli. They are not, it's not an energy equation. So I'm trying to stress all this basic and fundamental. Okay, so that's it for Bernoulli, which is chapter 3. A lot of time has been spent on it. Questions? Then we look at dimensional analysis. It's just a way to simplify our problem by reducing the complexity, and namely that we can take away 3 variables for any problem due to the pi theorem. And in doing so, you form a lot of dimensionless parameters, the pi terms. So primary dimension of mass, length, and time, and how you use similitude to do cheap experiment by matching all the dimensionless parameters, Reynolds number, pressure coefficient, drag coefficient, etc., etc. And from that, you can do model testing. Any question on that? Can you do any other problem that you may not have seen before? Yes?
Will we ever be doing any dimensional analysis where we're not just equating the Reynolds numbers?
What do you mean? I don't understand the question.
Like, so that you have the similitude thing there where we're just equating the 2 Reynolds numbers of the
Yes.
model and the prototype.
Mm-hmm.
Will we ever be doing anything that deals with things other than Reynolds numbers?
Well, if a problem, some of that you have seen in the homework, the problem statement did not include the viscosity as one of the variables, what does it tell you? What is it assuming in the problem if there's no mention of viscosity as an independent variable that will change the answer? What is that problem basically telling you? Assuming inviscid. So for that case, you don't even have a Reynolds number because viscosity is not in play. When you have at least 1 or 2 homework and example in class that deal with that. It's the assumption we make as an engineer, just to simplify the problem, and very often people do that. They assume inviscid just to get a feel for the problem, do some sensitivity study, and then they add viscosity, and the analysis get much more complicated, right? So to answer your question, if there's no viscosity involved, you don't even need a Reynolds number. But if there is a Reynolds number, this must hold. They must match. Otherwise, your model testing is totally irrelevant, right? Okay? Questions? Any more questions? Okay. So that's dimensional analysis. And from there, we move on to chapter 8, which is the pipe flow. And within that, we talk about laminar versus turbulent flow, chaos versus layers, and transitional Reynolds number. Laminar flow is very, very small percentage of real-life application, 2% of engineering problem. Majority of pipe flow, at least, is in the turbulent regime or turbulent area. And most importantly, we went through a very detailed derivation of the energy equation from your first law in the control volume in thermodynamics. And you should be comfortable with the origin of all the terms that is now casted in a way that is used for analyzing pipe flow. Very specialized form of energy equation that's only used in, seriously, pipe flow only, but very practical, because it relates to my frictional losses in terms of an increase in the internal energy or increase in entropy, that's the H of F, and whatever device machinery that had transfer work or in or out of my control water, pump versus a turbine, and that's this term. Are you comfortable with that? Yes?
So I know we had a problem on the homework that was due today that dealt with the non-circular pipes.
Yes.
So in those cases, should you be using hydraulic diameter for anything except for volumetric flow rate?
That's a very good question. The answer is yes. So rectangular duct, like the wood duct that you did for homework due today, we developed this concept of hydraulic diameter, which basically pretend that rectangular pipe now become almost like a circular pipe with a hydraulic diameter that is given by that equation. But that's only used for determining all the quantity except for continuity. In continuity, you will use the true area of that rectangular duct, which is the length times the width. Okay? Yes?
When you say like determining continuity, like do you mean like solving for like volumetric flow rate? Or okay.
That's correct. Solving for the velocity in particular, because the problem gives you the volumetric flow rate, right? 20 cubic feet per minute. And then you have to take that and calculate the velocity based on that. And the area you use to calculate the velocity is the one based on the true area, not the hydraulic diameter. That's a very important detail that I mentioned at the end of the lecture last time. But it's very easy to forget it. All right? Yes?
Are we only having like the shaft head when we have a turbine?
Correct. When you have a turbine or pump or compressor, a physical device that penetrates into your control volume, that actually have a shaft that allow you to add work or take work out. Otherwise, like a nozzle or a diffuser, remember we talked about that, like I'm blowing air. I can blow air the whole day and I cannot get any work out. Until you give me a windmill and I put in the flow path, and that is your shaft work. That windmill will capture the air and get work out of it due to rotation, and then you can use it for something else. That's the shaft work. That's very important to keep in mind. So some devices have no mean of getting shaft work out, like a condenser, a nozzle, a diffuser. Okay? A throttle valve, the one we just talked about, all it does is reduce pressure and create entropy. So the energy equation is very important, and we put it in the form, for pipe flow at least, very similar to the Bernoulli, but it's not. Friction factor is just due to Moody, Mr. Moody, you know. Yes?
Is there a reasoning for the signs of a pump versus turbine? Or is
We
it-
have a good question. So I may ask you that in the test. The question is, this W sub S, okay? For a turbine, what is the sign? Positive. For a pump, what is the sign? Negative. Now tell me why. This may be a question in the test. Now tell me why. That was the question, right? Tell me why. Yes? Say that again, louder, please.
The pump is doing work on the system, the turbine, the system is doing the work.
Okay. Essentially, the answer is go back from where this equation comes from, which is your first law for a control water, not a system, right? We have flow in, flow out. You have heat added, positive into my control volume, which we assume is 0. Then you have shaft work, which our convention is shaft work done by the control volume is positive. That's the contract we signed in the first law for thermodynamics. You have seen this, right, from thermal. That's a contract. That's something you sign on the dotted line, and we have to comply to it. And because of that, work out done by the control volume, like turbine, is positive. Contrary to that, work added to the fluid, like a pump or compressor, is considered negative. Do you have that? Do you get it now? And for the same reason, our contract say heat added is plus into my control volume. It's a contract. We just all agree on that. There's no argument. If you want to argue, then we change the whole foundation. Yes?
So are you just saying that we should expect our shaft work to be negative for a pump after we do everything else the same?
Yes. The sign will take care of itself. Like one of your homework, it asks you, well, like your quiz, it asks you, is this a pump or turbine? You don't know until you go through the whole energy equation. And then you let the sign tell you what it is. It's not obvious. Even though there may be a change in elevation, there's friction, you don't know whether it's a pump or turbine until you do this. Same with the homework where you have a pipe flow, no shaft, you have pressure difference, you have change in elevation, you don't know which way the flow will go. Remember that homework? Until you go through this. And the added caveat is X sub F, the frictional head loss, must always be what? Positive. That's it. And the reason is the loss of availability. So the X sub F is always a loss. It's an increase in entropy. Yes?
And for a compressor, shaft work would also be negative?
Well, compressor and the pump are devices that do what? When you have a pump and a compressor, what is that device doing? What does a compressor do? What does a pump do? How do you run a pump? You plug in the electric outlet and you consume power, and the pump will spin, and what the energy goes to? Increase the pressure of what? Of the fluid, the water. So that's obviously is work added from electricity to the fluid. And so compressor is the same. To run a compressor by itself, you have to have a huge DC motor. To test a fan blade out in the edge of the hallway, it may take about 1 megawatt of power. You have to put a huge DC motor and provide the power to run it. And that power is what being transferred from the fan blade of the compressor to the air that goes through the fluid. So it's work added to the fluid, and hence it's negative. Turbine is the opposite. Hydraulic turbine, the Crater Lake, the Smith Mountain Lake, the Hoover Dam, take water, change in elevation, and run it through a turbine to extract work. The turbine will spin by itself due to the gravity head change of the water, and that spinning motion is run a generator, like a power. Okay, so that's work done by the control water, and it's positive. Any question on that fundamental? Okay, the rest is really the key point is the energy equation and the good grip of it. The rest is just bookkeeping. Thanks to Mr. Moody, you know how to read the chart. And then you know how to use that to go this route, which is give me a flow system, geometry, length, etc. Give me a flow rate, Q, and I will tell you what pumping power I need, no matter how complex the system is. And this is what I call the schematic. Determine the Reynolds number, Loveless factor, Moody diagram, friction factor, put in the energy equation to account for other elevation change, kinetic energy, etc., and out come the power. Same old, same old. You do it once, you do it all. And there are example, which I will go through in the homework, where you don't go left to right. The example where the power is given, you go backward. That's some of your homework, which I will alert to after we take a break. So this is all you're responsible for test 2. Is that clear? Any question as to your responsibility, as to what may or may not be in the test? Yes?
So we won't be expected to do anything, would there be any overlap with test 1, like momentum?
Yes. There will be overlap in the sense of continuity. Would there be specific problem involving momentum? It might. I can't say no. Right? I mean, your SP1 involves momentum, so you have to prepare for it. Yes?
There's no minor losses on this test then?
There is no minor loss?
Or are there gonna be minor losses?
Absolutely. Everything until the class ends in half an hour will be your responsibility. Questions? Yes?
So for half the form note sheet, can we just write that under our previous tests?
Absolutely. Yeah, that's what I want you to do for your final exam also. Same sheet of paper except you can use the pen. I give you a 2 minutes break. When we come back, we just purely deal with